All right, so this is section 4.1 of Math 146. We're going to be talking about composite functions in this particular unit. And for the most part, most of this should be some kind of a review. But what we're going to cover is the concept more than anything else. We are going to look at a few examples, but more so concept, and also how to determine domain, because that can be one of the bigger sticking points. In general, a composite function just means it is a function evaluated within another function. So basically, you're plugging an entire function into every variable in the other function. The way we denote that is, there's two different ways. I am preferential to one specific way, but there are multiple ways that you can represent that. This notation right here is a very common notation. A lot of people refer to this as the fog notation just because it looks like it says FOG. The little circle in the middle is not really an O, but it does kind of represent the word of. This just means f of g of x. The notation that I am preferential to is this one, which says exactly the same thing, f of g of x. But in this particular notation, what you should see is that you're taking the f function, and I am literally plugging g of x into that function. It's just easier to see, I think, from a visual perspective, what that specific notation means. So a real quick example of what that might look like would be if we defined f of x to be 2x squared minus 3, and we defined g of x to be 4x. The idea is, if I want to find f of g of x, again, I will prefer this form, but you have to recognize both. That just literally means I'm going to take that g of x function right here, and I'm going to substitute it into every x in f of x. So basically, you would end up with 2. I'm going to put a parenthesis where the x was, and I am literally going to substitute in the 4x. And then we go about our simplification process. So f of g of x, let's see, if you square 4x, that's going to be 16x squared minus 3. So you're going to end up with 32x squared minus 3. That would be f of g of x. So we basically substituted the entire g of x function into f of x. Let's talk a little bit about the domain of this. In the example that we have here, you can see that g of x itself is a polynomial function. It's linear. It's 4x. And there is no domain restriction whatsoever on 4x. As you know, you can let x be any value that you want to. You're going to get out an output of a y value. If you look at f of x, it is also a polynomial, which in this case is a quadratic. Once again, you can put any value of x in you want to for the domain, and you'll get out a y value. So there would be no domain restrictions on either one of the two pieces. Therefore, there's going to be no domain restriction when you composite them. And it doesn't matter which order you composite them in. I could have done g of f of x, which would be going the other way around. So let's just show what that would look like real quick. G of f of x, well, that means I'm going to start with the g function, and where the x is, now I'm going to substitute the entire f of x in here, and then simplifying, distributing the 4 would be 8x squared minus 12. And you can see that that's just another polynomial that we get out. But again, there's no domain restrictions on any of this stuff because of the fact that both of them have no domain restrictions. They are all real numbers for both domains. Whenever you composite two things that are all real numbers, you're going to get a domain of all real numbers for both of them. It's when we have domain restrictions on one or the other piece that we have to be careful. So somebody once told me in this in this capacity that the way to think about it, and this was I thought was really good, that if you think about the domain as a bunch of tiles, and these tiles represent the numbers that you can have, that your input could be your x values. So let's say that you've got f of x, and f of x is all the tiles that I can put into that box right there. So I can put a whole bunch of tiles into that box. And g of x, likewise, has its own box of tiles. And I can put a whole bunch of tiles into this box right here. The idea behind this is that if I put all these tiles into g of x, but I'm missing a couple of tiles, like let's just make this easy. If I put all the tiles in g of x that are every possible number between 1 and 10, but I forget to put the tile for number 5 in, when I take that g of x box and I dump it into here, I still don't have that tile number 10. So I'm evaluating my function f of x by taking all the stuff that I could have had in g of x and dumping it into f of x. I still don't have that tile 10. Now, f of x may have its own issues. It might be missing some tiles or whatever as well. But that's the general idea behind this whole idea of a composite. So whatever you don't have in g of x still can't exist in f of x, if g of x, of course, is the composited function. It's the composite piece. So that's just, I'm hoping that that will resonate with you just a little bit. Let's take a look at algebraically how we're going to figure this out. So let's take an example that f of x is defined to be 1 over x plus 2, and g of x is defined to be 4 over x minus 1. I'll make that look like an x minus 1. There we go. So if we're going to look at f of g of x's domain, f of g of x, I'm not worried about doing the actual substituting the values in just yet. What you should have, what you definitely need to do is you need to look at your composite function first. So g of x is the composite function. It's the inner function. It's the one that we're substituting into something else. Well, you should be able to look at g of x and know from g of x that x cannot be 1. So that number 1 tile is missing from g of x. We have to eliminate that from the domain. So we know just by looking at g of x that x cannot be 1. Here's the part where it gets just a little bit tricky. It's not horrible, but if you look at f of x, you know that if it was just f of x and there was no composite function, that x would not be able to be equal to -2. However, we're substituting g of x into that x value. So what that tells me is whatever I have from here, this whole thing cannot equal -2, because -2 would cause a domain issue in f. So what you have to do is you have to set 4 over x minus 1 equal to -2, and whatever we get there is what we have to also eliminate from our domain. So we'll solve that for x. Multiplying both sides by x minus 1, you would get that -2x plus 2 has to equal 4. So keep solving for x, so subtract 2 on both sides. And then divide by -2. So we would get here that in this case, x cannot be -1. I probably should have used that symbol all throughout, because this is what x can't be. So we have to eliminate from our overall domain, f of x's overall domain, excuse me, f of g of x domain is that x cannot be -1 or +1. Okay, those are going to be your domain restrictions. And the notation that we use for that You could certainly use interval notation, so negative infinity to -1, and then union with -1 to 1, and then union with 1 to infinity. Your book tends to use what's called set builder notation or set notation, and it looks something like this. So there's the set notation. It's the set of all x. This vertical bar means such that, and then you basically just state the restrictions. X cannot equal -1, and x cannot equal 1. Okay, it's just a different way of writing the domain. So that would be your domain. All right, and that's the general idea behind this. So you have to figure out what the domain restrictions are on the composite first. Then you have to figure out, if you plug that composite in, what you cannot have based upon your outer function. So let's do another example, and we'll see if we can make this make some sense. So let's say that you know what? Let's actually use the same example, except we're going to do f of x. So now I'm actually going to look for f of x. So this time we are actually compositing the same function into itself. So we have to look at f of x as the interior function. So we know from, we know from 1 over x plus 2 that x cannot be -2. That actually takes care of the interior f of x. Now, we have to know that this whole thing right here is going to be composited into itself. So if you rewrote it, it would actually look like 1 over, and then 1 over x plus 2 plus 2. That's what it would look like, is the actual composite function. So again, the idea is that denominator can't equal 0. So in this case, this whole thing right here can't be -2. So I would have to set 1 over x plus 2 equal to -2, and then solve that. So multiplying both sides by x plus 2, you'll get that 1 equals -2x minus 4. Adding 4 to both sides, 5 is equal to -2x, and therefore x cannot be -5/2. I keep forgetting to write the cannot equal to symbol there. Another way to think about it would be, once you composite it, take that whole denominator and set it equal to 0. So you could take 1 over x plus 2 and set that equal to 0, knowing that that can't be the case. Of course, subtracting 2, you'd be right to that step right there. So in this case, your domain would have to not only eliminate the -2 from here, but it also has to eliminate the -5/2. So you would have the set of all x values such that x cannot equal -5/2 and x cannot equal -2. And that would be your domain. All right, we're going to do a really quick example that is actually asking us to show that the two composite functions are actually equal. Meaning, here's f of x, which is going to be 3x minus 4. And here's g of x, which is going to be 1/3 of x plus 4. So what does that mean about showing the composites are equal? We are trying to show that f of g of x is the same thing as g of f of x. So in order to do that, we basically have to do both composites. There's actually a good reason for doing this, by the way. So f of g of x, So we're going to take the f function, and we're going to substitute the entire g of x into where x was. So that's going to be 1/3 x plus 4. All right, let's see what we get there. So if we were to distribute the 3 into the parentheses, the 3 times 1/3 is going to go away, which is going to leave us with x plus 4 minus 4. And of course, x plus 4 minus 4 simplifies to x. Now let's do it the other way. Let's take the g function first, which is 1/3. Replace the x with a plus 4. I'm sorry, replace the x with a parentheses. Don't forget the plus 4. Now we're going to put into its place the f of x function, which is 3x minus 4. Following order of operations, technically you could distribute the 1/3, but let's follow order of operations. I think it'll make things easier. If you do the inner parentheses stuff first, 3x minus 4 plus 4 gives you 3x. Don't forget we've got a 1/3 out here, and then 1/3 times 3x, of course, is x. So these two things are indeed equal to each other. And the fact that they simplify to x actually has meaning, which we will talk about in 4.2. We're not going to get quite there yet. So that is showing that two composite functions are equal to each other. The last thing I want to talk about in this particular video is what is called decomposing a composite function, or at least that's what I call it. So we're going to call this decomposing, a composite. And there are multiple ways that we can do this, some of which should just hopefully kind of stand out and be a little bit easier than others. So the idea is, let's say that we are given some h of x function. And that's going to be, in this case, x squared plus 1 to the 50th power. What we're trying to do is we are trying to decompose this. We are trying to write h of x as some function f of g of x. Well, in order to do that, we need to figure out what the outer function f of x would be and what the inner function g of x would be. If you're given some kind of parentheses or grouping symbols, it's usually pretty easy to tell what your innermost function or your g of x would be. In this case, I think it's pretty easy to see that g of x is that inner piece right there, because that's something we plugged into that parentheses. So we're going to call g of x x squared plus 1. Therefore, the f of x part would be everything that's left. So if you basically just remove that x squared plus 1, you've got something raised to the 50th power. Well, the something still needs to be a variable because it's a function of x, so it is literally just x to the 50th power. And now if you were to kind of think about it, did that work? Well, if we take the process the other way, if I were to do f of g of x, I would be taking all of that, substituting it into that x, and I would be right back to x squared plus 1, that whole quantity raised to the 50th power. So this is what is called decomposing the function. This part right here is the decomposition of h of x, which was a composite function. It is very important that you start to be able to see what things could be plugged in to something else as a composite function and how that works. Again, that's a very, very important concept for calculus purposes. Let's go ahead and look at another one. So let's say that h of x is 1 over x plus 1. Again, there are multiple ways that we could go about breaking this down. One thing that I'm going to say, and I say this to all of my calculus classes, especially once they get to this point where we need it, a denominator is always a composite function. So when you have a fraction, whatever's in the denominator is a composite function. And the reason for that is, and hopefully this is something that you remember using exponent rules, I could actually write that entire denominator into parentheses, and I haven't changed anything. And technically that whole x plus 1 in the bottom is being raised to the first power. Well, if I were to bring that up to the top, we know that hopefully we know that that is going to be represented by a negative power. So that's the same thing as 1 times x plus 1 now raised to the negative 1 power. And hopefully that helps in the fact that you can now see, oh, that's in a parentheses where my power outside is like negative 1. So now you can hopefully see what your g of x and your f of x would be. Not necessarily to do everything that I just did there, as long as you realize that that denominator is a composite function. And if that's the case, then we could see that g of x would be the entire denominator. And if that's the case, then f of x would be 1 over, well, remove that whole thing in the parentheses and just put an x in its place. F of x would be 1 over x. And then again, you should be able to see that if you were to do f of g of x, then you would substitute the red x plus 1 into the orange x in the bottom, and you would be right back to the capital H of x. That is not the only way to do this, however. There are other ways that you could do it. Okay, this next way, and I'm going to stick with this exact same problem here. This next way is really trivial when it comes right down to it. Because what if we just wanted to say, oh, let's let g of x equal the function x? There's nothing wrong with that. It is a function. And if that's the case, then f of x, well, if I simply take out the part that I have for g of x, well, that's removing that x. Well, that just means I have to put an x in its place, would be 1 over x plus 1. Okay, that's very trivial. It's not the most common way of doing something like that, but that also works. We're actually looking for something more like the one on the top. You're looking for the entire x plus 1 to be your composite, but the one on the bottom is not incorrect. So how could we do that on the one on the left-hand side? Something like that. We're not going to go quite as trivial with x, but you could let g of x be x squared. So the one on the left, if we simply let the g of x be x squared, which is just this piece right here, that means the f of x, I have to rewrite everything that's there just without the x squared. So f of x would be all of that, and then instead I'm just simply going to put an x in its place right there. So now, once again, if you did f of g of x, you would simply take this, plug it in for x, and we would end up with h of x. So it's another way of doing the exact same problem. That one is not as trivial as just saying g of x is x, because we let g of x be x squared. But that's another way to decompose it. Again, we're pretty much looking for something like this because that makes the most sense, and it's really going to help you out with other things in the future. The only other thing that I want to mention, and I'm not really going to do much with, is you can add, subtract, multiply, divide, these things. If you add and subtract, you have to take into account the domains of each piece that's being added or subtracted. If you multiply or divide, then you obviously, especially with division, you have to take into account whatever the denominator would be of the two functions that you're dividing, because that's going to be your main piece. But I don't really think that's something we're going to come across too much, so I'm not really going to go through any examples on that. All right, I think that is plenty enough for 4.1. When we come back with 4.2, we'll talk a little bit about more why that those composites equaling x both ways was important. Yeah, that should be good enough.